Continuing with our theme of monitoring and looking into what's going on in our machines. Our next speaker is a remote speaker on Zoom from Socorro, New Mexico. We have Felipe Madsen, who's going to talk about not just how he's listening in on the universe with his radio telescopes, but how he's listening in on the computation that he's performing on them. Felipe, can you hear us? You might have to be louder. I think. Okay, I can see you, Felipe. I can't hear you.
Yeah, I was muted and I was on presentation mode, so I couldn't, uh, for some reason I couldn't unmute. So
Gotcha. We can hear you now. You're 5 by 5, loud and clear. So I'll hand it off to you. So over to you, Felipe.
let me share again. You were able to see my screen earlier, right?
We can see your screen, but it's I can see your notes and slides. There you go.
Yes.
Outstanding. Okay.
Go
Thank you.
back and yeah, thanks, Greg. And I hope the event yesterday was great. I'm sorry I couldn't be there in person this time. Um, I hope I can be there next year to see old friends. But yeah, let's talk about monitoring and diagnostics to understand how our workflows are doing and support scaling up. So I work as a software engineer for the Algorithms Research and Development Group at NRAO, and we've been developing imaging workflows for interferometric imaging using path and OSG resources for something like 4 years now, and we've been quite successful in why? Okay, we've successfully ran imaging runs, science imaging runs, and we're now scaling up. So this is an image of the VLA. That's one of the interferometers, one of the radio telescopes that we operate. And the VLA is in New Mexico and it's 30 antennas. And these 30 antennas work together to synthesize the behavior of one telescope, at least the imaging properties and resolution of one big telescope. In this case, the VLA can make images that are, in terms of resolution, with synthesize a telescope as big as 30 kilometers in diameter. But there's a lot of computing involved there, and that's why we need to go for distributed computing as our data volumes increase. And okay, so interferometric imaging is a computational problem. Interferometers are indirect imaging instruments, and we deal with sparse and irregular sampling functions. On the left here, there's an image, a map of the array configuration. Where are the antennas located? And that translates into a sampling function to the right that looks like a star. So a Y configuration translates into a sampling function that looks like a star. And the effect of that, the third image from left to right here, is what we call the dirty image. So it's an image of the sky that has artifacts that are due to the sampling function that has all kinds of contributions from the sampling function. And to remove those contributions, we run an iterative process that's basically a least squares minimization. And to get to the final image that's on the bottom right of this slide. We've been running, as I said, for a few years now. Since 2022, we've been running on Path. We have had some previous experience with CHTC, And we used our imaging workflows to make the deepest radio image of the Hubble Ultra Deep Field back in December 23. It was a combined effort with CHTC, OSG staff, and we got a lot of resources into that, topped at close to 100 GPUs. And we used those resources to make the deepest image of the Hubble Ultra Deep Field, as I said. And we had on that particular science run at 300 times speed up in imaging compared to a previous allocation on a high performance computing system. Our imaging process is iterative, as I said, and we run like from 10 to 100 GPU jobs per what's called imaging cycle. And this imaging cycle repeats updating model and then updating and then subtracting this model from data and resampling data. This runs about 10 to 15 times per workflow, so to make one image. And so we run like hundreds to thousands of jobs to make one single image. But these jobs they're not all independent. They follow a loop. They follow loops of 10 to 100 jobs. There's like an order of 10 to 15 gigabytes input files per job, and we are now planning and actively working on a scale up to multiple imaging workflows working concurrently. We expect the number of jobs to increase by a factor of 100. On the right here, I have a panel showing some our presence on the OSG, how many jobs, how many CPU and GPU hours. And so why monitoring is important for us? Well, especially to improve our throughput. Well, our distributed jobs, they're computing images from parts of our data. But in every imaging cycle, we have to put all these images together to make one image and then run some processing on this one image and then scatter this data again, subtract model from data, and go through the loop again. But we usually have like unfortunate jobs that will, due to slow transfers, disconnections, all kinds of problems that a job is subject to. They have a significant impact on the workflow at all time because we are running like hundreds of thousands of jobs, but in groups of at least a factor of 10 smaller. So a problem on the job here will impact the wall time of the entire workflow. So checking job execution times, data transfer times will help ensure reliability, stability of the system. And also making simple image quality checks and convergence, that this iterative process has to converge. And we have to check if it is really converging. Otherwise, we'll be wasting cycles on images that will diverge and will not be useful to us. We better stop the process at that point and check what's happening, see what we can do to make sure images converge and we have useful images. So that way we save time and resources. So that's basically why we really want to monitor very tightly our jobs. And what do you use for monitoring? Well, of course, the basics, kind of watch queue when you launch like thousands of jobs and you want to know where you're at. Kind of watch queue with our imaging workflows have at least 3 nested DAGs. And so sometimes it's a little hard to parse the output of Condor Watch Queue, but it's very useful. Then Condor Queue, like you see to the right here with dash DAG and dash no batch, gives a nice tree view of the jobs, their relation, and what's happening. And well, You see the uh, you see the help jobs there, which is basically what we want to understand and get understand why and get rid of to make our also make our workflow execution as autonomous as possible. Then, of course, I grab all my Condor logs for return values that are not zero. And I wrote recently in scaling up, I wrote this very simple check workflow script that will give me really simple statistics. How many jobs are completed? How many jobs are failing? What are the eviction rates? Why are these jobs evicted? We recently made our jobs very impatient. Like if they have any signs of disconnection, we want to retry these jobs instead of waiting to see if they will be able to reconnect. And we also want to periodic vacate the jobs based on the non-runtime that we know they should have. If they are going above that, we want to remove them. And this with this tool, we can keep track of that. And now we go into some more some graphics monitoring tools. This is a really useful panel that I check that I use to check my resource allocation on NRP. A good fraction of our jobs is running on NRP, and with these tools, I can really dig into the resource allocation, how many GPUs I'm using, how I'm using those GPUs, and how much memory I'm using on the pods. Well, this was about a year ago. We were scaling up single imaging workflows, and we were having lots of jobs taking too long to transfer or getting on hold, ultimately getting on hold because of that, or just delaying the workflow. And we came with this simple plot that shows the time that the job is executing on the x-axis versus the time that the slot is busy with that job on the y-axis. And the red circles there show outliers that shouldn't be there. The red line shows is like if the time slot busy that is the time execute is 80% of all the time that the job is that the slot's occupied with the job. And so if the points are spread around the red line, they're kind of healthy. But if they are way to the top, like what I circled there, it's not. So this shows how we. So I showed this plot to OSG, CHTC, Path staff, and we discussed, that these are taking too long transferring data. So these jobs cannot be healthy. And sure enough, we iteratively found problems, and we just came it went from the left ultimately to what we see on the right. The aspect ratio changed on that one, but it's there's a lot less. That's way less outliers on that one. Jobs are a lot more healthy, and that's one good example of how we used this kind of plotting visualization to help also to improve our workflow execution, and at the same time help improve cache configurations, server configurations, and whatnot. This is an old visualization that I developed to look at how my jobs are running in terms of as a function of time. So here there's time on the x-axis. So this looks it is pretty much like a Gantt chart for but it's showing jobs on different sites. And it's but here there is also domain specific information that I want to detach from this tool. So this is the first version of this tool, and I'm working on making this domain agnostic so that it's useful for more people. And if I want to add the domain specific, I can. But this is showing basically transfers in yellow, and then the job execution in blue. And the red is the domain specific part. But this is for one single image. And if I run this for multiple images, I now just color coded by what image I'm running from which input data. And and then I can see how my workflow is processing different images as a function of time. And I can see idle time on this one. I cannot see transfer time right now, but I can see idle time, and I can go dig on why there's idle time, what's holding back my workflow run. This shows this is just job index as this is for a workflow that ran 1,024 jobs. So it's just job index on x-axis, and it's showing the red bars on the top are really the job execution time, but the blue bars are overhead. And it may look like this workflow is terrible, but it was this workflow is fine. It was accessing like 30 GPUs per cycle, and so and all the overhead here is jobs that were waiting on other jobs to finish, and so the overhead build up. But accessing more resources will shorten these bars, and there's no outliers. There's not really like bars, really large negative bars here, which would show like individual jobs that would be problematic. And we've used this to find such a thing. Now, this shows how many resources I have as a function of time. And this helps us, look, if the plot on the left, we see that there's like only one GPU allocated towards the end of the run, towards the last 5,000 seconds on the run. That's only one job, basically one job running. And why is that? Because that particular job had problems, was an unfortunate job, as we call it, and it was being retried several times, or it was on hold for a long time. And when we see this plot and identify that kind of thing, we can work on identifying what is causing that and working on resolving that cause, so that we have something that looks like more like the plot to the right. And this is by the way, for different runs of the same workflow. And you can see that one took like over 20,000 seconds, and the other was a lot healthier. They're accessing this roughly the same number of GPUs, at least the same maximum GPUs is 45 there, is a little under 45. Uh, but the job on the right is a lot more healthy because we studied the job on the left and applied everything we learned to the workflow on the right, which was ran a lot faster and used the resources a lot better. So to conclude, monitoring and diagnostic tools are critical to support workflow efficiency. These tools that I presented have been used to actively identify infrastructure issues and validate solutions, find workflow inefficiencies, and develop optimized configurations, advanced development of domain applications. And the current model for these tools that I showed is I run local scripts to collect data on the AP, and then I have a local notebook on my machine to process data and generate these plots. I'm working to make these tools more accessible to others, easier to share and all that, more flexible and really domain agnostic, so that they can be useful for the community. So let me know if you would like to use and or contribute to this. And that's what I had to show today.
Uh, Thank you, Felipe. I think we have time for one or two quick questions. Anyone from the audience or online? If not, let's thank Felipe again. Sorry.
I had one back here.
Uh,
So Felipe, I know the graphs give a lot of details that you're able to really dig into, understand individual stuck workflows or jobs or things doing a lot of I/O. Do you have a metric that evaluates the overall workflow performance? I mean, do you have a 0 to 100 type number, or A, B, C, D, F kind of grade for the entire thing that kind of summarizes the approach?
Not
Because,
yet.
but
That's a good idea. I don't have like a right now. I don't have one number that would summarize that. It's a great idea. I will think about it.
because it'd be interesting to see, what do all the, grade C workflows look like for the detailed stuff versus the grade A type ones.
Yeah. Thanks.
Okay, let's hear it for Felipe and NRAO.